All right, hey everybody. We are starting this video where we left off the last one. We were looking at a specific example. S is the half-open interval from 0 to 10. And what we saw is that we examined three different open covers of S, one of which, this first one, admitted a finite subcover, and the other two did not admit a finite subcover. And in particular, this example here, I think, really was a great one to sink our teeth into. So this was an example of an open cover of S that did not admit a finite subcover. What I'm going to do now is erase some of this, but then turn the page literally, or I guess figuratively, turn the page to discuss this new idea that is illustrated in this example. Okay, and here we are. So the new definition that we want to deal with is the definition of this, this idea of compactness. So compactness is a quality about subsets of the real numbers. In this case, it's these examples S. So let S be a subset of the real numbers. Then we say S is compact if and only if every open cover of S admits a finite subcover. Right? So this is a challenging definition because it's a definition about a set S, but its definition implies that every conceivable open cover F that we can think of necessarily admits a finite subcover. And from what we've seen already, there are lots of weird or interesting open covers that we can create. So let's examine this idea of this, the set S that we saw below. So again, S was equal to, let me grab my pen here. S was equal to the half open, half closed interval from 0 to 10. We looked at three different examples of open covers on the set, and we saw that two of them did not admit a finite subcover. In particular, this was an example of an open cover. It completely covered S. We saw that here. And yet, it did not admit a finite subcover. This is what we talked through in the previous video. Because of that particular example, we can definitively conclude that S is not compact. Right? And let's think through exactly why that is the case. We have the definition of compactness above. A set S is compact if and only if every open cover admits a finite subcover. And therefore, we can think through what it means to not be compact. And we could say a set S is not compact if and only if there exists an open cover that does not admit a finite subcover, right? So the definition of compact was a statement about every open cover, and therefore it's not compact if and only if there exists a counterexample, open cover, F of S that does not admit a finite subcover. Okay, and having negated the definition of compactness like that, we see definitively, that this F is not compact, or I'm sorry, that this S is not compact because we found the existence of an open cover that did not admit a finite subcover. Now, a brief word on how we often use the definition of compactness. First of all, it is very hard to prove that a set is compact using this definition, right? Because to prove that it's compact, you would have to prove a statement about every open cover. And that's really challenging, right? We've already seen there are weird open covers you can create. And so it is quite hard to rigorously prove that a set is compact using this definition. However, it's not that hard, relatively speaking, to show that a set is not compact, right? You just have to find this counterexample open cover. So oftentimes we will try to show sets are not compact by hunting for a clever open cover to use. Or if you're trying to definitively show that a set is compact, oftentimes we'll have to make an argument by contradiction, right? We'll have to assume that it's not compact, therefore assume that there exists this counterexample open cover, and use that to construct some sort of contradiction. So going forward, we're going to be looking at a lot of great theorems that involve this definition of compactness. And we'll go from there. So thanks so much for watching this video. I will see you in the next one.